Section 8.2 and 8.3, we're going to do this together because it really is the properties of parallelograms, and these are actually biconditional theorems. And rather than learn all of the theorems today and then in the next section learn all of the converses are also true, we're going to just cover it all in one. So we're going to talk about properties of parallelograms in this lesson. We're going to try to understand where the properties of parallelograms come from, and we're going to use those properties to solve for missing sides or angles for certain parallelograms, and we're going to know what it takes to prove a quadrilateral is a parallelogram and disprove whether one is a parallelogram or not. So this is the definition of parallelogram. It's a quadrilateral with both pairs of opposite sides parallel. So we have these sides are opposite and parallel, and we have these sides are opposite and parallel. That's what a definition of a parallelogram is. And you probably already know some things about parallelograms from past math classes. So take a look at this parallelogram with both pairs of opposite sides parallel and make some conjectures. What do you think is true about the following, like opposite angles? What do you think might be true about these angles? What do you think might be true about consecutive angles, like this angle and this angle? What do you think might be true about opposite sides? So think about that and see if you can justify why. We'll actually be proving some of these as well as we go through. So if some of your conjectures were correct, a quadrilateral will be a parallelogram if and only if both pairs of opposite angles are congruent. So what we have learned here is, and maybe this is what your conjecture was, but both pairs of opposite angles here have to be congruent. So if I tell you that it's a parallelogram, then you know that both pairs of opposite angles are congruent. But it's vice versa also. If I can show you this quadrilateral without any markings or words that it's a parallelogram, and you can see that both pairs of opposite angles are congruent, then it's a parallelogram. Remember that if and only if, you can switch the hypothesis and conclusion around and you'll still have a true statement. So you can start with one and finish with the other, or you can start with the conclusion being the hypothesis. So another theorem, theorem 2, a quadrilateral is a parallelogram if and only if all consecutive angles are supplementary. So angle X and angle Y are consecutive, and when we add them together, they will be supplementary and add up to 180. Or these consecutive angles, Y plus X, are supplementary. And again, if I tell you that you have a parallelogram, then you know the consecutive angles are supplementary. Or if you can see in the quadrilateral that the consecutive angles, both pairs, all the consecutive angles are supplementary, all of them, then you know that it's a parallelogram. The third theorem is a quadrilateral is a parallelogram if and only if both pairs of opposite sides are congruent. This is probably the one that you made the best conjecture on because it's pretty common. But again, if I tell you that it's a parallelogram, then you know that both pairs of opposite sides are congruent. But if I just give you a quadrilateral with the sides marked opposite, congruent, then you know it's a parallelogram. And those are really the difference between our section 8.2 and our section 8.3. And the fourth theorem, a quadrilateral is a parallelogram if and only if the diagonals bisect each other. And again, if I tell you it's a parallelogram, then you know the diagonals bisect each other. On the other hand, if I can show you that a quadrilateral has two diagonals and they're bisecting each other, then you know that it's a parallelogram. All right, so let's use some of these to find some missing values. Okay, first of all, notice that we have a parallelogram by definition because we have both pairs of opposite sides are parallel. So we have a parallelogram. So what does that mean? Well, what it means is that consecutive angles are going to be supplementary. So that means that 2x plus z is equal to 180, but I don't know z. So let's try to see if I can find something else. I also know that 2x is equal to 50. because opposite angles have to be congruent. So that means 2x has to equal 50, so x is 25. Okay, so I found the value of x is 25. Now I can go ahead and put 25 in here. So 2 times 25, or we know that this angle is 50. So 50 plus z equals 180. So just subtract 50 and z is 130 degrees. And last but not least, I can find y right here, because y, its opposite side is 18, and so y plus 3 has to equal 18. So then y is equal to 15. So I found the values of x and y and z. Okay, well now we can do kind of the same thing, only we're going to make it a little more complicated. This time it doesn't have it marked as a parallelogram, but it says the measure of one interior angle of a parallelogram is 50 more than 4 times the measure of the other angle. So here's an interior angle. Okay, here's another interior angle. One of them is 50 more than 4 times the measure of another angle. So if this angle is x, then the other angle is 50 more than 4 times x. So now what we can do is use the fact that this is a parallelogram. They told us that. And so in a parallelogram, remember, these angles are supplementary. So that means that x plus 4x plus 50 has to equal 180 degrees, supplementary. So this is 5x plus 50 equals 180. And again, subtract 50 and divide by 5, and you will get x equals 26. So what is the measure of each angle? Well, we have x equals 56, and that means this angle is also 56. And now we could literally just subtract from 180. So 56 from 180 is 154. Or you could substitute in the value of x. So we have found all of the angles. All right, so let's prove, if we only know, and this is one of the properties, so we're not just going to say, well, it's a property, it's a theorem, but could we prove it? So if BD and AC bisect each other, could we prove that it's a parallelogram? Could we prove that both pairs of opposite angles are congruent? Well, look at what you have here. You have this angle right here is congruent to this angle right here because of vertical angles. So what you have is you have this whole triangle right here is congruent to this whole triangle. So we have triangle BEC is congruent to triangle DEA because of side angle side. That's one way we can prove those triangles are congruent. Well, if the triangles are congruent, then remember, every corresponding angle will be congruent. So now I could say that angle CBE is congruent to angle ADE. And if that's true, then BC has to be parallel to DA by the alternate interior angles converse. So I just proved these two sides are parallel. Well, now I can go back and do the same thing here. I can prove these two triangles right here are also congruent because, again, we have vertical angles. And so now, once I prove those two triangles are congruent, again, through CPCTC, then I would also be able to show that this angle right here actually I want to go with this angle right here, sorry about that. And this angle right here are congruent and then by alternate interior angles converse, now it proves that if alternate interior angles are congruent, then you have parallel lines. So that's just kind of a walkthrough proof explaining how you know that because the diagonals bisect each other, it proves that you have opposite sides both parallel. And the same is kind of true here. We didn't use this as a property, but what if you're only given that BC and AD are parallel and that BC is congruent to AD? So what if you're only given this information of parallel and congruent? Is it enough to prove? Well, it is, because again, if you have parallel lines cut by this transversal right here, then your alternate interior angles are congruent. And if your alternate interior angles are congruent there, then you can prove the triangles are congruent because you have this reflexive side right here. So now you can prove that this triangle right here and this triangle right here are congruent by, so you have congruent triangles by, again, side, angle, side. And once you have congruent triangles, now you could also show that their other corresponding angles are congruent. So this angle right here and this angle right here are corresponding and congruent. And again, if you have alternate interior angles, now we can show that these two are also parallel. So kind of similar to what we did. And I'll put in the notes, I'll give maybe a little bit more detailed information on that proof. So it turns out we have an additional theorem for parallelograms that says if one pair of opposite sides of a quadrilateral are both congruent and parallel, so the opposite side, one pair, both congruent and parallel, then it is a parallelogram. Remember, anytime we say it's a parallelogram, all of those other properties apply. So these are the ways that we can prove a quadrilateral is a parallelogram. We can show that both pairs of opposite sides are parallel. That's by definition. We can show both pairs of opposite sides are congruent. We can show both pairs of opposite angles are congruent. We can show one pair of opposite sides are both congruent and parallel, and we could show the diagonals are bisecting each other, and that would be an additional way that we could prove that quadrilateral is in fact a parallelogram. So, can you draw a figure with the same properties of this quadrilateral that is clearly not a parallelogram? And just because I've drawn it like a parallelogram, do you have enough information? And the answer is no, because if I have this side right here, the same as this side right here, they're still the same length. But when I connect the other two sides, it's clearly not a parallelogram. Well, what about the other one? What if you had one pair of parallel sides and one pair of congruent sides, but they're not the same? They're not opposite like we were given. Well, yes, you can have parallel lines like this, and you can have these sides be the same, and that's an isosceles called an isosceles trapezoid. So yes, you can. So how about, could we say if these are parallelograms or not? Do we have enough information to say? Well, we just drew an example for number 1, okay? On that last screen, we drew parallel lines, and that is the same, but that's kind of our counterexample. No. Okay, so what about the next one? We have opposite sides congruent. Both pairs of opposite sides are congruent, and it just happens to be that both pairs of opposite sides are both congruent, but they happen to be all the same. But that's still okay. Okay, how about this next one? Do we have enough information for number 3? Well, we have parallel lines, and we have one pair of congruent angles right here. So we have one pair only right now of opposite angles congruent. That's not enough. But remember, you have these parallel lines, okay? And you have the exterior angles here with a linear pair. And so this angle right here is the same as our angle inside. And same with this exterior angle right here. And so what we end up having here is, because of linear pairs, these two angles also have to be the same. So this is also yes. And number 4, we only have one pair of sides that are congruent. So again, could we draw a counterexample for this one? I think we can. So if we just have two sides that are the same length, we can draw, again, something that is not a parallelogram. Okay, in this next example, it says, show that quadrilateral ABCD is a parallelogram. So if you plot those points, -3, 3, that's A, and then B is 2, 5, C is 5, 2, and D is 0, 0. Now we're not just going to say, oh, it looks like a parallelogram. So what are some ways that we could prove it? Well, one way that would be kind of easy is, we could prove that the length of BA is equal to CD and that BC is equal to AD. That's one way we could do it. Or we could also, a second way we could do this, well, there's multiple ways. Another way we could do it is we could find the slopes of AB, and if it's congruent to DC, that means the lines are parallel, and that AD would be the same slope as BC. If we have congruent slopes or equal slopes, then those two opposite sides, both pairs of opposite sides, would be parallel. You could also use the, we already did that. You could also just do one pair of, another way you could do this is you could find the slopes of AB and DC and make sure they're equal or congruent, and then also that AB would equal DC as far as length. So there's multiple different ways to do it. And so what you would do is you would actually calculate those things out. So I'd like you to pick one of those ways to prove or show that it's a parallelogram, and then you can check the, and maybe you have a different way, and that's fine too, because there are other ways to do it. Remember, we summarized all of the ways to prove. But those are probably some of the easier ways, and then you can check back and make sure that you have done it correctly. But we don't just graph it and say, oh, well, it is because it looks like it. Well, no, not quite. Okay, so now it says, given that ABCD is a parallelogram, prove that CD is equal to AD and AB is equal to CD. So I kind of walked you through some proofs. I'd like you to try this on your own. You don't have to do a 2-column proof. You can do just a paragraph proof, but let's see how far you can get on this one on your own. And then again, you can find the information in the notes to see whether you have done it correctly. The last example we are going to do here is we are going to find what would be the fourth set of coordinates for D right here that would make the figure a parallelogram. So if we graph -1, 0, that's A. B is 0, -4. C is 8, 6. 8, -6. So now where would D be? Well, we know that the sides have to be parallel, so we know that the slope has to be the same. So if you just think this through, if we find the slope of AB, it would have to be the same as CD. So we could find the slope. And you could do this algebraically for sure and set up an equation, but we could just think about it. To go from A, or let's go from B to A, we went up 1, 2, 3, 4, and we went over to the right 1. So do the same thing over here. 1, 2, 3, 4, over 1. Now our slopes are the same. And so we could just find that ordered pair for D, which would be 1, 2, 3, 4, 5, 6, 7, negative 2. Okay? And so that is your fourth coordinate that would make it a parallelogram, because now you have the same slopes. And you could check the slopes for BC now and do the same thing. Otherwise, since you found the slope of AB, so you know the slope of AB is equal to, we went down up 4, so it was negative 4. So now we could set that equal to in our slope formula and set that up algebraically.